Is Divakar there?
Yes, I am there. Just a minute.
Okay, okay. Just share the screen.
Okay, wait. Just a minute. I need the website. Okay.
All the conveners here for other conferences can share the screen to show something or the website.
Okay, I am sharing the screen. Yes. Is it visible?
I think Vivek sir has joined again.
Okay, a couple of minutes.
Is it visible, Tina ma'am?
Yeah, it's visible.
Just.
Vivek sir has already joined. Okay.
Yes, Vivek sir has joined.
Just 1 or 2 minutes.
Just one line you say, Divakar, and then we will ask Vivek sir.
I would just take a couple of minutes. Okay, this is our upcoming conferences. ICCAES, that is International Conference of Chemical and Environmental Sciences. That is also organized by Basic Science and Humanities Department, Institute of Engineering and Management, Kolkata. It will be also on the online platform. It would start from 18th of December till 20th, 3-day conferences, totally in the virtual mode. And we have a galaxy of speakers here as well. Divakar, just show the speaker list. If you can scroll down. It is covering a wide aspect as well. From all the core part of chemistry, that means the chemical sciences, starting from quantum till the organics, nanotechnology, biochemistry, environmental sciences, all the segments and integral part of the subject is covered. I will just take 1 more minute to show the list of speakers. We have also a galaxy of speakers here. Divakar, if you can show. Key dates are not important here. We do not need to display the key dates.
And one more important thing is the paper will be selected paper will be published in Web of Science based journal.
Scientific, yes. It is a peer reviewed from the Web of Science. And just if you can show the page which is displaying the speaker list.
I have already shared the speaker list screen in my computer, but it is not showing actually.
I guess Vivek sir has joined, so let us start the session.
We have speakers from Japan, UK, and all over the world. And D.D. Sharma sir is also there. So all are cordially invited. It would be another conference in the virtual platform. Thank you. So let Vivek sir share his screen.
Yes, Tina, you start and let him share the screen meanwhile.
Shorishtaman, start. Yeah, Shorishtaman sir.
I'm audible now.
Yeah, you're audible. Yeah.
Okay, so we are starting the technical session 3 of Spectrum 2020, and I welcome our dignified guest today, Professor Vivek Polchet here. So before we start his talk, I'd like to give an introduction of Professor Vivek to the audience. So Professor Vivek Polchet here, after his PhD in 2005, worked as a postdoc in France and USA for a few years before starting his own independent group at KAUST in 2009. In 2013, he moved to TIFR and his group is working on the development of novel nanomaterials as catalysts to tackle climate change. He has published nearly 100 articles with H index 54 and around 12,600 citations in reputed journals like PNAS, Nature Communications, Angewandte Chemie, Chemical Science, ACS Nano, ACS Catalysis, etc. He is the recipient of the prestigious O-RISE Research Fellowship at US EPA. He was awarded as top 25 cited author in 2011 by Tetrahedron and Young Scientist Award at DCL 2012. Professor Vivek also received an Asian Rising Star Lectureship at 15th Asian Chemical Congress, ACC, Singapore in 2013 from Nobel laureate Professor Eiichi Negishi. In 2015, he was admitted as a Fellow of Royal Society of Chemistry, United Kingdom. He was awarded Bronze Medal by Chemical Research Society of India. He was also recognized as Emerging Investigator Material Science and 175 Faces of Chemistry by Royal Society of Chemistry, UK. Professor Vivek was also awarded the prestigious Materials Research Society of India MRSI Medal 2019 and Fellow Maharashtra Academy of Sciences. In 2020, he received Young Research Awards in Nanoscience and Technology by DST Government of India. With this brief introduction of Professor Vivek, I would request Professor Vivek to start his talk in today's session. The title of his talk is Nanotechnology to Combat Climate Change, Transforming CO2 to Fuel and Waste Plastic to Chemicals. So over to you, sir, and welcome once again to this forum.
Thank you very much for your kind introduction and also the invitation to deliver a talk. So am I audible? Is there an issue?
Yes, it's perfectly fine, sir.
You're perfectly audible.
Yes, sir,
Okay.
audible.
Okay. So the talk, the way I prepared is because I heard that the audience is from various subjects, not only the chemistry. So it's more a general public talk, but at the end of the talk, I will try to go into more technical details of some of the results that we recently obtained from our lab. So the talk will be about use of nanotechnology to combat climate change. I will try to brief about the nano, then about the climate change, and then I will try to explain how one can use these nanoscience or nanotechnology to combat the climate change. And if time permits, I will try to explain the use of nanomaterials for waste plastic to chemicals. So I guess everyone ideally knows the nano. So it's 10⁻⁹ meters. So it's ideally a scale like a meter, centimeter, micrometer. It's just a scale, right? And this is one of the bookish definition where it says that any material which is 1 nanometer to 100 nanometer in particle size is considered as a nanomaterials, and you study them, so it's a nanoscale science. Ideally, this definition by itself is not really correct, right? Why it's only 100 nanometer? I can have a 101 nanometer. I can still call it as a nanomaterials, right? So we'll not go into that, but this is a general definition that everyone knows or everyone agrees. So why the scale matters? But if you look at the scale, if you look at the Earth, it is around 12,000 kilometers. So I need to reduce that size to say around 100 lakhs to get you the football, and I have to reduce that size to say 100 crore times smaller to get you a nanoparticle C60, which is around 0.7 nanometers. So you can imagine how small it is. Another way to understand the size is if I have to measure the human length or a main length, then it will be around billions of nanometer. The cells that we all know about are thousands of nanometer, whereas atom, which is the small in the material part of the science, is around tens of nanometers. So if you have 10 hydrogen atom horizontally arranged, you will get around 1 nanometer. So it's really small. This is another way to again see the same thing. Now it's not about the scale, but it's about that when you transform the bulk material, the material that you see around, into the nanoscale, they start showing unusual properties. For example, We know the gold, the jewelry and everything that we wear, those are yellow shiny colored. Why? Because the gold is metallic. The electron cloud on the gold surface reflect most of the light except small portion of the blue light, and that's why it's yellow in color. Whereas as soon as you convert that bulk gold into very small nanoparticles of different particle sizes, based on the size, the electron cloud which was reflecting the light, now at a nanoscale start oscillating with the electromagnetic field of the light. It's not reflecting, but it's oscillating, and at one particular wavelength there is a resonance. We call it a surface plasmon resonance, and that gives you a different colors of the gold. So you can make gold of a different color. Another example is melting point, right? If you again take the example of gold melts around 1064 degrees Celsius, but if you make a nano gold of around 2.5 nanometer size, you see it start melting at 300 degrees Celsius, a dramatic decrease in the melting point from 1064 to 300 degrees Celsius. And if you look at this small cartoon, you will see that when you have a bulk gold, you have a less number of surface atoms and more number of a bulk atom. Whereas when you go to the nanoscale, you have more and more atoms on the surface, right? Because of the smaller size and higher surface area, surface energy. Now it's easy for you to move these atoms away from these three atoms, right? Because it has to only break 3 coordination or 3 bonds. Whereas for the atoms inside has to break around 6 bonds or 5 bonds. So you need more energy for atoms to move inside within the bulk. Whereas when the atoms are on the surfaces, it's difficult. It's easy to move them, right? Increase the bond length. You need a lower energy, and that's how the melting point is low when you go to the nanoscale. It's a simple explanation. Another one is the tensile strength of the material. We all know that stainless steel is one of the strongest, but now look, the carbon nanotube is around 100 times stronger in terms of the tensile strength as compared to the stainless steel, and it's lighter, right? People are already using these helmets which is made up of carbon fiber. Now the question is why the nanomaterial shows unusual properties. So one of the simple explanation is the surface area. So whenever you look at any material, bulk or any nanomaterial, you always divide the surface into two. Divide that material into two components. One is the surface, atoms are on the surface, and one is inside the bulk. And you will see in a general bulk material, you have most of the thing inside and very small portion on the surface. For example, if I look at this coin, then it has around 10,000 or 100,000 internal layers versus only 2 surface layers. If I cut that coin, 2 mm coin into 1 mm, then I double the surface layer. I have a 4 surface layer and around 5,100 internal layers. Still a very small portion. Whereas when you go to the nanoscale, look what happens. If I take a 1 centimeter by 1 centimeter cube, the surface area will be around 6 centimeters square. If I break that 1 centimeter cube into 1 millimeter cube, then the total surface area will be 60 centimeters square. There is an increase, but not much, 6 to 60. However, if now you reduce the cube size from 1 mm to 1 nanometer, you see that 60,100, it's a large surface area. There's a huge surface area. So that's the difference. That's the difference. When you go from a bulk to a nanoscale, there is an increase in the surface area. And when I say increase in the surface area, what happens? You have most of the atoms on the surfaces, right? So they will have a low coordination number. So the atoms will have a higher number of uncoordinated bonds. We call it as dangling bonds, which provides them high surface energy and makes that surface really reactive. And then that's why it reacts and shows unusual properties. In addition to that, there are several other things that happens, quantum confinement and several other things, energy level splitting, that allows you to tune the optical properties of that material in addition to the physical properties. So how do we build them? They are so small, then how do I build them? There are 2 ways to build them, synthesize them. One is top down, where you take a gold ring that you wear and break it down until you reaches the very small size of the nanoparticle. Obviously you cannot do it manually, but there are instruments where you can break them to smaller particles. It's possible to make a nanoparticle, but it's expensive and you don't have a control over the size and shape. So the top down is not generally used. Then another technique is bottom up approach. As name suggests, you start with the atoms or molecules, and then you force them to meet and react, condense to form nanoparticle. And as soon as nanoparticle is stopped, you stop the reaction. It's some sort of a chemical reaction where you stop as soon as you get a nanoparticle. So now, since you are doing a reaction, between the two molecules or within the same molecule. You will have a control over how many molecules they react, how they react, how much time they react, and we can have control over the concentration, temperature, addition, and all of that allows you to then make a nanoparticles of different sizes, shapes, morphology. And that's why generally bottom-up technique is used to make nanoparticles of different kinds. Another question is, how do I see them? They are so small, right? You cannot really use a visible light. So you need to use some other light which is smaller than the nanoscale, the nanometer. And that light is electron beam. So you create the light of electron beam, and now you take a material and expose that material with electron beam and see either the transmission image or a scattered image. So there are two ways by which you can see the material using electron beam. It's either called a transmission electron microscopy or a scaling electron microscopy. It's like a conventional transmission light microscope and confocal laser microscope. So both the technique uses electron beam. One technique uses transmission electron to generate the image. Another technique uses either the scattered electron or a secondary electron to get you the image, and which gives you very different information of the same material. This is how the TEM looks like, and this is how the transmission electron images looks like, right? So you get a sizes, you can get a shapes, you can see whether they are monodisperse or crowded. You can get the distances. You can even you get an atomic resolve for HRTM or STEM. You get a highly resolved images, and you can even see the atoms, and you can see distances between them, how they are organized. That way you can get the crystal structure of that material. You can also see the defects. See, something is missing here, so that means you can also see the defects in the material. So there are several other things that you can do by transmission electron microscopy. This is a scanning electron microscope, and it gives you more surface information, more morphological information. So something like this. This is a cobalt oxide. This is the TiO2. You can get a very nice surface morphology. This looks like a stacked sheets forming those spheres, or stacked cubes to form those spheres. And nanomaterial or nanotechnology is no more just a science of a basic research, but it's already started making its impact in a consumer world, and there are several products that is already being used. For example, quantum dots. Dots are actually a nanoparticle with a very small size, and that's why we use the word dots. And it has a very strong quantum confinement effect, and that's why you call them quantum dots. So ideally, these are like, say, metal. These are the nanoparticles of cadmium selenide or zinc with a zinc sulfide shell. And this is one of the very first discoveries in these nanotechnology in 1981. But now we already started using these quantum dots. You must have seen the QLED TV in the market, which uses a quantum dot. Another example is carbon nanotube, which is discovered in 1991. One of the strongest material, still lightweight, and that has been used in different electronics, lithium-ion batteries, concrete, and there are lots of use at a research level. This is more commercial level. Another one is graphene, another magical material with excellent conductivity as well as the flexibility. So one day you can get those flexible phones, right? Foldable phones using the graphene. Simple TiO2. If you coat the TiO2. Mix them in the paint and then paint your walls, they will start purifying the air. This is already demonstrated in this particular building. So you can think of all the statues in India can be coated with these nanoparticles, and they start purifying our airs, right? In addition to other things. The quantum dots are also used for detection of the diseases at a very early stage. And this is another excellent example of nanomaterials in medical science. Okay, so that was very quick about the nanoscience. Obviously, for those who don't know much, for those who know, please ignore or excuse me for that very basic thing. Then what about climate change? I guess we all know about the climate change. We see that in the TV every day, in the news. And I think everyone wants to do something about the climate change. So let us see what is climate change, and then I will come back to nanotechnology to see how one can solve the problem of climate change. So this particular slide, which is Earth's energy budget, ideally explains the climate change very well. So we all know that the energy that planet Earth is getting is from the sun. So our life is ideally dependent is on the solar energy, right? So you get a solar energy, some of that energy get reflected, some of that energy get absorbed, and once the planet absorbs that energy, again they emit the secondary, again they reflect some energy and start emitting some energy, right? See here, emitted surface energy is around 398.2, and that energy is most of the time is in the form of infrared radiation, right? And so if you have something in the environment which trap that infrared radiation, then those infrared radiation will not go out of our environment, and that will cause the heating. That is exactly what is happening. CO2 is one of the molecule which absorbs those infrared radiation and stop them from going out of that environment, right? And that's why more the CO2, more will be the trapping of these emitted light, and you will keep warming the globe, right? So if I have more CO2, it will be a more global warming. So CO2 is one of the key greenhouse gases. In addition to the CO2, you have a methane, you have nitrous oxide, and even we can consider water vapor is something which capture the infrared radiation. So all of these causes the global warming. CO2 is main culprit because it has a long lifetime, very stable sp hybridized molecule, so it doesn't react with anything. So it has a long lifetime, and unfortunately we produce lots of that. So that is the real cause of the climate change. Right, this is what I was explaining. So the upgoing that the external radiation that is produced by the planet after absorbing the solar energy is in the form of infrared radiation. So any molecule which capture absorbs the infrared radiation, ideally considered, can be said as a greenhouse gas. But then you have to also bring in the lifetime of these molecules, their concentration in the environment. So in that sense, it's water vapor, carbon dioxide, methane, nitrous oxide, right? So some of these are the greenhouse gases. So you can see here up to 1950, the ppm of the CO2 concentration is around 300 ppm, and after 1950, when you have this industrialization and some sort of a path towards the artificial life, you see a sudden jump, and now we are around 415 ppm, and it may be increased now in last 2-3 months, which is the highest recorded CO2 concentration in the history of the planet Earth. So that is increasing the temperature. You can see now systematically there is an increase in the temperature with increase in the CO2 concentration from 1888 to today. So this animation shows the Arctic Sea ice, which is around 7 millions of kilometers. Please look at the unit. It's 7 millions of kilometers. Now from 1980 to now around 2015, 50% of that is gone. 50% of that is melted, and you are around 3.5 millions of kilometers. So such a dangerous effect of climate change or global warming on the ice. And obviously, if the ice melts, what will happen? The sea level will go, sea level will rise, and then all the cities around the sea will have a serious effect, and that will have a secondary effect on other cities, another part of the planet. So this is a very recent paper in Nature.com. It's more a theoretical model, but they say that if we go by this way, if we keep increasing the CO2 concentration and the global warming rate is the way it is today, the Mumbai, which looks like this, will be like this. So which seems to be very serious, and we need to do something to stop these. In addition to that, we are in a COVID-19 era, and the climate change has a direct relationship with all these diseases. Scientists from NASA and several other institutions have discovered bacteria as old as 8 million years, and this recently they found that some of these are resistant to all the 18 types of antibiotics, the best top 18 types of antibiotics that we have. So imagine if these bacteria come into our life and infect us, that will be even more dangerous than COVID-19, because COVID-19, there was already several other COVID family of the viruses. So we know some science about them, about those viruses. But what about something which is 8 million years old come into our life? We have no science, we have no information about those bacteria, and we may not be able to deal with them. So there is a direct impact on our health because of the climate change. So is it too late to stop the climate change, or we can do something? So there are several answers for that. one can say, oh no, this is how the planet Earth is. We are going to extinct. This we are not able to stop. That's one way of thinking and enjoying the life. Another way is trying to fight with it, trying to combat the climate change. Obviously, you need to have a societal change. We need to save the energy. We need to minimize the waste. Several other things. But what about the science? What can science do or technology do? So one of the science is a nanoscience or a nanotechnology. And if you really look at the very simple solution for the climate change is you somehow capture all the CO2 from the environment, because CO2 is the main problem, right? So if I capture all the CO2 and convert that into fuel, useful chemicals, right, or a food even, the way trees does, right? Trees capture the CO2, use the solar energy, use the water, and get you different products, different food products. Can we do the same thing? Can we create artificial photosynthesis, which will do the same thing? And that's where the use of nanotechnology can come in, because we know that whenever you change the material to nanoscale, they show a dramatically different properties, and you have a excellent handle on tuning and controlling the properties of these nanomaterials. So how do I do that? So this is how the life is, right? So you get energy from sun, we produce lots of CO2. Now we have more industries, more cars, more vehicles, so you produce more and more CO2. Ideally, all that CO2 is taken care of by the trees and the ocean. But since we have produced too much of CO2 because of the growing population, growing industries, neither the trees nor the ocean is capable of taking care of that CO2. We must plant as many trees as you can, but there are lots of studies which clearly shows that any number of trees you can plant, you cannot take care of the CO2 because it's too much already in the environment. How do I solve this problem now? You think about something called artificial trees. No, which are the trees which does the same function like trees: capture the CO2, harvest the solar energy, capture the water from the environment, and split that water into hydrogen and oxygen, and you react that hydrogen with CO2 to get you fuel or a product. So artificial trees is again a fancy word. Ideally, it's a material. Ideally, it's a nanomaterial which will have these ability of CO2 activation and conversion into chemicals. Another way of saying this is like this: you have a car, you fill your car with CO2 and keep driving it all your life, no more filling. This looks again crazy, but if you look at the science, it's possible. You fill the car with CO2, I create some sort of a catalytic system which capture that CO2, and using the sunlight and the water vapors from the environment, convert that CO2 into methane or methanol. So methane is your CNG, right? When you fill the gas in your car, that's ideally 98% methane. Now you converted CO2 to methane by freely available solar energy and the water. Only catalyst is required. Once you form the methane, again the routine thing, you burn the methane, get the energy, drive your car or your industry or whatever the function that you want to do. You get back the CO2. Now you don't release that CO2 into the environment, capture it again, and in that catalyst and convert back into methane. So it's a cyclic process where you go get the CO2 to methane, burn the methane, do the function, do the work, drive the car, and again get back the CO2, which is not going into the environment, but back into your catalytic reactor, a cyclic process, right? With a CO2 neutral or a methane neutral. So nothing is going into the environment. And I will show you at the end of the talk that this is very much possible, at least at the lab scale. So how do I design these artificial trees? How do I design these nanocatalysts which has the ability to capture CO2, harvest solar energy and react that hydrogen gas coming from the water with CO2 to produce methane and methanol? So this is what we do in our lab. The way we do it, we have a 3-component system. You need a support of some very high surface area material. Then you need active sites, which has the ability to capture the CO2 and activate the CO2, capture the hydrogen or water and split water into hydrogen. And then you also need energy, and we want the energy to be coming from the sun. So you can convert that solar photon either into the heat and do a thermal catalysis, or you can convert those solar photon into something called hot electrons. I will try to explain that afterwards, and transfer those hot electrons to the CO2, activate the CO2. Now it's easy for CO2 to react with hydrogen, something like that. So this is what we do in our lab at TFM Mumbai, and I'm going to show you some of those examples. So first thing that you need is catalyst support. So this is the material that we discovered in our lab. So this is a pure silica, SiO2, It's like a purified sand on the beaches, but it is a nanoscale and it has this dendritic fibrous morphology, and that's why we call it as a dendritic fibrous nanosilica, a DFNS. We can prepare the nanoparticles from 50 nanometer to 100 to 150, up to 1200 nanometer size. Surface area is also very high, from 500 to 1200 meters per gram. For example, if I prepare a nanosilica for 600 nanometer, the surface area is around 500 meters square per gram. What is this? It's like if you take a 1 gram of a powder in your hand, it's like a 1 football ground in your hand. So that's the huge surface area that can be used for different application in addition to the catalysis. Excellent thermal stability, so you can heat them up to 800 degrees Celsius, or you can do any activity, any processes which needs 800 degrees Celsius. Stable up to 130 MPa, so one can do a processes which needs high pressure, and it's easy to synthesize. If you look at this Nature protocol, where we wrote this step by step how to synthesize using simple labware like London flask and heater and something like that. We even have the videos how to make it. So if you plan to make it, it's really easy. You can make different kinds of these DFNS. So these are the SEM images. I showed you that one can use the SEM to see them. So you can see they're very monodispersed. And when I say fibrous silica, the fiber is more like a petal rather than the hairy fibers. These are the TM images, again showing the fibrous nature and monodispersed nature of the material. And the important question that we ask in our lab is, what is the reason why I get these type of structures, these type of fibrous shaped spheres rather than something else? So this is explained by this particular animation. So these are the template molecule. The blue ball is quaternary nitrogen, and that zigzag line is a CS2 up to 16th time, a non-polar tail. So what happens whenever you add these surfactant molecule into the solvent? Here we're using water and xylene. They try to minimize the total energy of the system by self-assembling and forming these lamellar phases. To minimize the repulsion between these quaternary nitrogen, we added one more co-surfactant, say pentanol, having this polar OH, red ball, and again the tail, and you stabilize those interfaces. Now what we observe that these lamellar phases are not floating flat into the water or into the solvent, but they are in the form of a droplet, bicontinuous microemulsion droplet. Bicontinuous because we have water and xylene solvent, and these are the droplets, which are made up of just a CTAB and toluene and xylene and some amount of pentanol. So these are not nanoparticles, these are the reactor, these are the template where I grew my nanosilica in those channels, right? So now if I keep these droplets away from each other, I get a very small nanoparticles. However, if I force them together and some of them merge, you get a bigger droplet and I get a bigger nanoparticle. So this is how we tune the particle size. We can now get from 50 nanometer to 1200 nanometer by simply changing some reaction conditions, so that sometimes they stay away from each other, sometimes they merge based on the requirement of the size of the particle. So this is our own material invented by our group, and we have a US patent and then several other patents already filed, and we use it for catalysis and CO2 capture and conversion mitigation. Whereas there are other 150 groups worldwide who are using this for a range of application in drug delivery, sensing, energy storage, and energy harvesting. So quickly, how much time I have? Can anyone update me?
Sir, actually time is over.
Time is over, okay.
Wind up as you can.
Okay, then I will just take another 2-3 minutes. I will not explain anything, I'll just show what we did in recent times, okay?
Yeah, please, sure, sir.
Okay, so some of the recent finding from our Nanocode group is, one is the black gold and coal heating. So this is the example where, the term artificial trees, where we prepare the black gold, which harvest the solar energy and convert that into photons and hot electrons that can be used for converting CO2 to fuel, or seawater to drinkable water. Another example, I skip all of this because I know I was late, so I lost the time. Another one is the perfecting imperfection, where we use defect as the catalyst. We created the defects in the silica material, and we showed that those defects work cooperatively with each other and again convert CO2 to methane. So this was one of the first example of metal-free, ligand-free CO2 conversion process. Another example that I want to show you is here. The waste plastic to chemicals, the plastic is one of the serious issue that we all are facing. It's not only on the surface, but they are also in the air, and when there is a rain, these microplastic is going into our body ideally. So we showed that one can design a solid acids which has a strong acidity like a zeolite, but the porosity like amorphous aluminosilicate, which can take care of these plastic and degrade back them to chemicals from where they are prepared, and then you can use those chemicals for different application. Okay, and then we also work on CO2 capture. So we develop a material, we capture the CO2 from the chimney, and this can be at a room temperature, or we recently developed a capture which can be done at 650 degrees Celsius. So as soon as it is formed in your reaction, just capture it. Don't even come out of your chimney. Okay, so I'm sorry for delay. So this is the conclusion. Nanotechnology can help us to take on the challenges of energy and environment and protect from the climate change. I like to acknowledge my group and the funding by DAE and Shell and several other funding agencies. And I like to thank you all for listening to me. And I'm again very sorry for the delay because of some issue with my computer. Thank you.
Okay, thank you very much, sir, for your insightful talk on the use of nanotechnology to combat climate change. So the forum is now open for questions, and I already have some questions on the chat box. So let me ask the questions one by one. Sir?
Yes.
So the first question is by Professor Arno Basu. What is the advantage or disadvantage of pseudospin in graphene?
Oh, I have no idea. I don't work on graphene. I'm sorry.
Okay. There's one more question, sir, by Arno Basu. What are the best available electrocatalysts for carbon dioxide reduction?
Okay, that's a good question. There are several. I think one of the best, or my favorite, is copper-based catalyst. People are using these copper and changing their shape and support, and that is giving not only methanol but even the C2 products. They are able to change the selectivity and the total productivity of the materials. Copper-based catalyst could be one of the best one for electrocatalytic CO2 conversion. What we do is we do a photocatalytic or thermal CO2 conversion, not the electrocatalytic.
Okay, so thank you very much, sir. I go to the next question. This is by Professor Tina Day. How can nanotechnology be used for artificial photosynthesis?
Yeah, this is what I was trying to explain. So artificial photosynthesis is nothing but you have to develop a material which has ability to, harvest and activate the CO2. Right, it's like a capturing, and activating is like bending the CO2 a bit so that it becomes reactive. Then again, harvesting the solar energy and using that photon to get you hot electrons and heat. At the same time, split water into hydrogen and oxygen. So and use that hydrogen, those electrons and the CO2 to get you different chemicals. Right, that's artificial synthesis, and that thing can be done using the concept of nanotechnology. I try to show you some, like the black gold and TiO2. These are some of the examples where you can do that.
Okay, so there is one more question by Professor Tina Day. Is this niche technology economically viable for a developing country like India?
Right now, maybe the economical viability is a question based on the process that you're talking about. For example, we recently developed this black gold. So you will say, okay, gold is very expensive, so why do I use the gold to convert CO2 to methane? Perfectly right. But let us say I'm using that gold in a very small quantity, and I'm using repeatedly for thousands of time, and I'm able to convert large amount of CO2 into fuel. Then that becomes viable, right? So at this stage, obviously everything is at a research level, but that's the main goal of all the scientists, right? To get you a economical and sustainable process. So it's independent of which country it is, right? It has to be viable everywhere, which is going to happen in few years possibly.
Okay, thank you, sir. There's
May I ask you a question? Oh, sorry.
Yes,
sorry.
Please. So please, you can ask your question.
I just asked a very small question. Good afternoon, sir, for your excellent presentation.
Good afternoon. Thank you.
My question, sir, is you see, 3D printing is also an upcoming and growing industry for technology, since the tensile strength of some nanomaterials is much more than that of steel and iron. are we considering any material for 3D printing, especially for the automobile industry?
Okay, again, it's out
That
of
is my
my
question.
expertise. I don't know, but people must be using the nanoparticles for 3D printing. I really don't know that how they're doing it, but must be doing it.
Thank you, sir. Thank you, sir.
Okay, so I move on to the next question by Pradeep Kashyap. How to measure exact distance between two atoms in HRTEM? How to choose exact center of atom from HRTEM for measuring distance between two atoms?
But you visualize the atom, right? And then you take the center. So I'm not getting your questions. Where is the problem? When I see the atoms, obviously this is only possible if you really have a proper high resolution TEM, right? By the corrected TEM instrument. When you see them, you will able to measure the distances between the particles, right? Exactly same, and that's what. And even these distances can be tallied with the distances that you get from the crystal structure using crystallography or XRD techniques.
Okay, so there is a next question by Shaborna Ghosh Dostidar. Sir, is it possible to capture all the CO2 present in the atmosphere?
Yes, ideally it's possible. It's not that science is known that how to capture the CO2 from the environment. But the question is, can we do that economically, sustainably? That's the question, and that thing is not done. Otherwise, it's possible. If you really have, if you're rich and you can give me all amount of money that is required, you can definitely capture. But the problem is, whatever the material that we have, they capture very small amount of the CO2. So you need a large amount of material, which will make entire process unsustainable. So that's the way research is, that can I make a material which captures large amount of CO2, very small amount of material and large amount of CO2. And by the way, what I was trying to tell you in my talk is capture is not a solution for the climate change. It has to be capture and conversion. Whatever the CO2 we capture from the environment has to be converted into some useful chemicals. Otherwise, it is not going to solve the purpose.
Yeah. There's one more question by Pradeep Kashyap. Can SAED indexing be done without XRD knowledge of material?
Yes, ED is done without XRD knowledge for sure, but then to analyze the data coming from the SAED, I think you need to have the XRD information, right? Otherwise, if it is completely unknown, then I don't know. If you don't know the distances between the plane or atomic arrangement of your material as such, then I don't know how do we index the SAED.
Okay, so thank you very much, sir. I don't see any more questions in the chat box, but still, if anybody else has any other question, can unmute yourself and ask directly or write in the chat box. I guess there's no more question. Then we can close this session. So once again, thank you very much, sir, for your wonderful presentation. And before we close this session, I would like to request Professor Dibakar to share your screen, and we would like to present a virtual memento to Vivek, sir.
Okay.
Professor Dibakar, are you here? Yeah, so it's here for you, sir. So in this pandemic situation, there is no other way for us than to provide you this virtual memento. So that's for you, sir.
Thank you very much. That's very nice.
Okay. So once again, thank you very much for your nice and very much insightful lecture. And it was very useful, a lot of useful information for our students also. So we will close this session, and I would like to, so please stay back with us, I would request. We will have our next talk now by Professor Joachim George from University of Lisbon, Poland. So Professor George is already here with us. So before I request him for the speech, and Professor George, I would also like to request you to present your screen in between.
Okay. Can you hear me?
Yes, sir. You're perfectly audible. Just kindly
Okay.
share your screen.
Can you see my screen?
Not yet, sir.
Not yet, sir.
Okay. Not yet. Oh, I need to activate screen sharing somehow.
Yes, sir. Screen sharing you must activate.
Present now. Your entire screen. Screen one. Share. Google Chrome. Sorry, I'm having a problem with the permissions of. I will have to re-enter the meeting.
So you can go to the present now at the bottom right corner of your screen. There will be finding the present now button.
I did find that, but I have a problem with permissions from Google Chrome.
Okay, so yes, sir. Your screen is being shared now. Yeah. Yeah. Your PPT is also visible. Yeah. Thank you very much, sir.
Okay, thank you very, very much. I'm not sure how much time I do have.
Yes, sir. So just let me introduce you to the audience once for 1 or 2 minutes, and then I request you to start your talk. So Professor Joachim George is from the Department of Computer Graphics and Multimedia, School of Engineering, University of Lisbon, Portugal. So Joachim George received his PhD from Rensselaer Polytechnic Institute. He coordinates the VIMMI research group at INESCID and is a full professor of computer graphics and multimedia at Técnico University of Lisbon. He is the editor-in-chief of the Elsevier journal Computers and Graphics, a fellow of the Eurographics Association, a distinguished speaker and distinguished member of the ACM, and also IEEE senior member. Professor George served on the ACM Europe Council and chaired the ACM SIGGRAPH Specialized Conferences Committee. He has organized 40+ international scientific events, was IEEE 2020 and Eurographics 2016 papers co-chair. He has served on 200+ program committees and co-authored 300+ publications in international peer-refereed venues. His research interests include augmented and virtual reality, medical applications, advanced user interfaces, 3D visualization, and modeling. So the title of today's talk by Professor Joachim is Approaches and Challenges to Virtual and Augmented Reality in Healthcare and Rehabilitation. Okay, so over to you, sir. With this introduction, you may please start. Thank you.
Thank you very much for this kind introduction. And I would like to introduce you to labor of love that we've done in the past couple of years in my university. Sorry, I'm just not seeing the information for the meeting. If you allow me a few seconds more before I start the presentation proper.
Sure, sir, no problem. Please take your time.
Google Meet. Oh, excellent. Thank you for this nice invitation. So, as you said, I have this. I'm heading this research group at Lisbon, Portugal. I'm a professor at Instituto Superior Técnico in Universidade de Lisboa, and this is a joint work with two colleagues of mine, and I'm not even mentioning the medical partner here. I just would like to call your attention for that we are organizing IEEE VR 2021 next March. Maybe not in this nice place, but probably virtually. As we know, we have problems with international travel these days, which brings challenges and opportunities. And I'm here to talk about the opportunities. So the idea of using virtual reality in medicine is not really new. There have been many attempts at using this since the inception of virtual reality more than 30 years ago. Why are we still talking about this, and why is this such an exciting research topic? Because only right now we are getting the hardware and the computing power capabilities that are needed to make this this a reality. And I would like to talk to you about the possibility of the reality virtuality continuum, a term that was introduced by my colleague Milgram in the 1990s. In that, you say there is not just a point, an immersion. A virtual reality is more than just full immersion. There is a whole spectrum of possibilities, from diminished reality, where we selectively wipe out parts of the real world around us, to spatial and see-through augmented reality, where we can see virtual objects against the background of the real world around us, through augmented virtuality, where we are immersed in a virtual world, but we see images of the real world around us to avoid us from stepping into obstacles, or to have an awareness of our environment and the people that surround us, to semi-immersive VR, where we see virtual worlds, but we can still raise our eyes and see the world around us. And we can call this spectrum of different opportunities of visualization mixed reality. And then we have virtual reality, which is the fully immersive world. And we have opportunities for applying all these technologies to medical applications, from diagnosis through patient care, through surgical planning, until surgery proper. Conventionally, we have focused on training doctors and on teaching anatomy and surgery. But, the interesting thing for a computer scientist like me, developing applications of virtual reality, is to try and establish dialogue with the doctors, building a network of healthcare professionals, identifying their current practices, and overcoming the differences in terminology. Usually doctors have a very big picture, but they have no idea on how the computer technology will help them. And they have this idea that they can provide the big picture, and the computer scientist can come up with an instant solution on the next day. And the next day usually takes something like 2 generations. We are entering now the fourth decade of applying virtual reality to medicine and augmented reality and related technologies, and the subject remains as timely as ever. You see, we have developed imaging technologies thanks to the advances in medical image that can provide very detailed images of the body. And computer science and computer graphics and visualization have provided fantastic ways of visualizing the human body structures and anatomy in 3 dimensions and now even in 4 dimensions. But there are many competing technologies that you can see here for visualizing different parts of anatomy. And there are interesting challenges there. We have used extended reality for learning. Now you can see virtual images in detail of the human body in great detail using augmented reality and virtual reality glasses. And we can use large display surfaces such as virtual tables for collaboration. How can we take advantage of these wonderful virtual reality techniques to make it possible to visualize the real world and to make these technologies available for surgeons. And one of these experiments we did was with radiologists. Oh, sorry. I just had to get rid of this pesky screen. So, the idea here is how can we use virtual reality to improve radio diagnostics? And radio diagnostics are usually done having in attention the illumination conditions of the room. And these can be sensitive to several conditions. We published this work in a conference called ACM Special Interest Group on Human-Computer Interaction a couple of years ago. So what's the problem that we're trying to solve here? Is to use virtual reality to improve the diagnosis of bone fractures and other problems using conventional imaging. The problem with visualizing these images has to do with varying illumination conditions. The fact that you can look at the display from a different angle can induce diagnostic errors. And people usually make these visualizations in rooms with special illumination and using monitors with specialized characteristics that make them really expensive. We thought, wait a minute, if we use virtual reality, we can control the illumination conditions because the people will be using our immersive headset, and we can control all these problems. So let me show you a small video of the experiment that we did. You can watch this video on YouTube. And so what you can see here is that we used a digitizing, optical digitizing surface we chose this apparatus so that radiologists could use familiar interfaces that require them to rest their hands on the table and not make them raise their arms in anatomically and ergonomically impossible postures. And so this frame can capture the gestures of up to 16 fingers on a table without need for specialized equipment. And this way, people can make simple gestures to navigate through the slices of a 3D dataset that you are seeing here, to rotate it and to adjust the viewing configurations to be most comfortable to them. You can adjust brightness in the virtual environment by using a simple display, a simple gesture. And we made the interface very simple on purpose so that people could easily translate their skills at interpreting images and focus on the task of visualizing the data set and come up with an interpretation of what they were seeing in anatomical terms. And this was familiar and make it very easy for people to follow, for radiologists to follow their workflow while having controlled access and not being distracted by spurious reflections on the screen or by tilting their head with respect to the monitor, since on purpose we made the visualization always follow their field of vision. So this is one advantage where we can use virtual reality to improve visualization conditions and control the visualization without being distracted by external factors. Okay? So what makes this experience unique in terms of computer scientists is that we did evaluation with real radiologists, 5 of which, so we tried with different specialities. Several of these people had no experience in visualizing virtual reality. We did try this out with an expert in radiologist, another expert in neuroradiology, gynecology, obstetric surgery, and dental implantology. And only one of them had experience in VR. And what they realized is that they complained about the resolution of the Oculus display, but we believe this is not going to be a factor because in the future, virtual reality displays will vastly improve to the point that we'll have a superior resolution even to today's full screen displays. And this will help people improve their diagnostics. Of course, these are still preliminary results, and we are working on doing a much larger data set with more specialists, which is notably difficult because people tend to look at us in the medical profession and ask why should they spend time trying to work out on a better, improved surgical or diagnostic instrument instead of trying to save lives by doing actual diagnostics. So this is not easy to get large numbers of actual clinicians to work with us. So I can answer the question. There's one person that asks, can virtual reality be a substitute for real-life experiences? Well, the point that I'm trying to present in this presentation is that virtual reality can improve real-life experiences, and you can use virtual and augmented reality to improve medical practice from diagnosis to actual medical procedures, and that's our Shangri-La, and even to post-operatory, to have a full life cycle improvement. Yes, some of the applications answering to Mr. Pradeep Kashyap, it's possible through smartphones. Yes, I have examples there. How do I think virtual and augmented realities can impact learning applications such as soft skills development? oh well, they can, they do, and they are. What is the difference? And I'm going to present an application in anatomy shortly on how we can improve the teaching of anatomy. So bear with me for a while. While I present another diagnostics-related application is virtual colonoscopy. The problem with virtual colonoscopy and diagnosing gut diseases such as cancer and polyps and other problems is that usually you have to go through painful and obtrusive diagnostics such as colonoscopy. And you can improve this using imaging techniques. Instead of actually inserting a tube in the patient's colon, you can extract a 3D medical visualization of the insides of the abdominal cavity, and then you can reconstruct the surface of the colon and navigate it using virtual reality. Why is this better than conventional imaging? Well, visualizing conventional medical images in 2 dimensions makes it very difficult and problematic to identify features. And people spend hours by looking at 3D on a conventional flat screen and cross sections of the abdomen. And what we want here is to make it to make diagnosis a first-person experience. You are seeing here Soraya, second-year PhD student of our lab, visualizing the colon, the reconstruction of the colon, and what you're seeing on the wall, that's her visualization of with virtual reality glasses. So this is what she's seeing. She is wearing a virtual reality headset and a pair of locator devices, and here you can see 3 different stages in which she can navigate the colon and visualize it from the outside and from the inside. And this is advantages relative to conventional techniques. We've published this a couple of years ago as well. Let me show you the video on how these interactions occur. So since she can navigate the whole colon through a map from the inside and outside, and using her whole body, she can visualize the whole organ without having to resort to conventional mouse manipulations. And this is the part of the value, a big part of what virtual reality offers you. You can visualize the in 3D, and you can control the point of view just by moving your head and your body around. And that's very important to improve the visualization as to a conventional desktop experience. And so we did a professional assessment of this with 5 male plus 2 female doctors. And what they say is that one big advantage of this diagnostic medium is that they can perform a full analysis of the colon and diagnose diseases in minutes instead of hours. They appreciate the sense of immersion, the freedom of movement that was afforded by virtual reality, and the possibility that they could navigate the world in miniature. They complained a little bit about camera control, and we identified several improvements, and we are working on a second version of this. So the take-home lesson from this experiment is that you can actually improve diagnosis using virtual reality in several significant ways as compared to conventional settings. And one important feature of this is that you can make diagnosis tools more affordable, and you can also make it possible to make remote diagnosis and collaboration more effective. And my next example is speaking to Mr. Arnab Bazu's question is, How can we improve teaching of anatomy and other surgery-related specialties through virtual and augmented reality? And this is, I'm going to present now an augmented dissection table that addresses a central problem of teaching surgery and teaching anatomy. You see, from the early classical ages, teaching anatomy was done by dissecting cadavers, and it has always been a collaborative effort. As you can see here, you have the master, but you also have the students and colleagues and collaborators who can intervene and discuss and have a virtual, the dissection experience has a collaborative shared experience. How can we improve this using virtual reality? Well, you know, one central problem with dissections today is that there is a shortage of human bodies, of dead human bodies, of cadavers, given the many anatomy and surgical schools that have proliferated throughout the world. Fortunately, we have now digitized corpses that allow us to visualize the human body in 3 dimensions. And how can we take advantage of that? Well, let me present you the work that we've done last year called Anatomy Studio, which allows people to improve augmented virtual dissection using mixed reality. What you see on this screen is a person, in this case Mauricio, just finished his PhD degree, using augmented reality glasses that's seeing on top of a table something that is not really there. And what you have is other people around the table can see conventional sections of a body and locate different slices across digitized human. This is slice number 4680. And you can have several people around the table sharing different views and a collaborative 3D session, and sketching on slices like this. This is a frozen cryosection of the virtual Korean. This is a frozen human body of that person that has been cut into very thin slices, frozen, and then photographed. And you can convert this to 3D images and visualize these 3D images using augmented reality headsets, as you can see here, tablets, access to a common computer, and being able to interactively doing digitization sessions. This video shows what you can do. So you can see both the slices and the sketched and the sketched contours. And this is very important for anatomy students that they are able to identify the details of anatomical slices and to visualize how these coalesce into forming 3D structures such as bones, vascular system, nerves, tissue, muscles, and different organs, etc. So people can navigate the slices on their tablets, and they can have a shared vision, and they can collaborate both on the tablets by sketching and visualize these on the tablet. And we've done experiments with anatomists in pairs to see how effective this technique could be. Here's an example of an anatomical structure. And we observed what they could do and what their different specialties. And what we could see is that they could find a big advantage in the sketching contours on the tablet, doing a mixed reality preview, that's the second image, being able to move their head around in order to explore the anatomical data set and collaborate and interact with each other by using a shared point of view. And this was a big advantage, that you can have several people around the table, each one operating on different slices and collaboratively converting these into 3D anatomical structures that are then rendered using three-dimensional computer graphics. And the conclusions were very positive. This work is being extended and with French colleagues on the University Paris Descartes. And we are together writing a book, sorry about the low resolution, a book on digital anatomy that will be coming up, edited by Springer. Moving on. So I hope, Mr. Dr. Arnab Basu, that this addressed part of your question. Now, the interesting issue about virtual reality and its applications to medicine is moving from the teaching to taking virtual reality to the operations room. And this is part of some very exciting and ongoing research work. And so part of this is, how can we interact with the computer in a germ-free environment, such as the operating room? That's part of the question. The other part is, how can we use virtual reality and augmented reality to improve visualization during laparoscopic procedures? Let me address these two things in separation. So first is, how do you do contactless surgical navigation? Well, one of the ideas is to use two-dimensional gestures to navigate 3D volumes. Of course, the problem is that you cannot use a mouse and keyboard, so we are using a depth camera and gestures. You track the body of the surgeon or around the table using depth cameras, and then you can control 3D volumes by making gestures from a distance, zooming, panning, etc. And we did make the anatomy of analogy to a Nintendo game box to make this work. Here is an example of using the feet to make it possible to activate the viewing modes. And what you see there is a clinician visualizing a 3D data set using their hands while sitting in front of a display. They can use the foot to activate the visualization, and they can use the hands to control the visualization, and then can use the foot again to deactivate the visualization. Notice that nowhere in this procedure the surgeon or any of the clinicians needs to be in touch with a keyboard or a mouse that would necessarily need to be disinfected to be free of germs. Now, the other part is, how can we improve visualization in minimally invasive surgery? You know, minimally invasive surgery is the procedure where doctors operate indirectly. Instead of opening the patient, they make two small incisions in the abdominal cavity, and then they operate while they visualize the field of operations to a camera. How can augmented reality improve laparoscopy? Here you see the typical operating room. You will notice that none of the doctors around the table is actually looking at where the instruments are. They follow the surgical procedure to these screens. And this takes a while to learn how to coordinate hand and eye movements, because they are not looking at their hands, they are looking at the monitor screen. And sometimes these postures can be really bad for your health. So what we are now trying to do, and working with surgeons, is to put head-mounted displays and using augmented reality to improve their visualization conditions. So instead of looking at the screen and operating on the patient, such as you can see in this image, or this one, you can have people directly looking at an augmented reality image of the innards of the patient that's been provided by the cameras inside the abdomen. And this is an example of what the surgeon would be seeing. And this would allow them, using the same contactless interface, to position the video feed from the laparoscopic camera inside the abdomen of the patient, and being able to control this visualization and look at their hands, and using much more ergonomic postures. This is the subject of several working research projects that we are conducting with a clinical facility in Lisbon, Portugal. So here is what we are doing. So if you are having a virtual reality headset, you can visualize the theater of operations, while at the same time you are able to access medical images from the same patient and try to connect one data set with what you're seeing on the camera. Our long-term vision is to approach image-guided surgery, where surgeons can use 3D images to match what they are seeing to the laparoscopic camera. And notice how we can use the feet of the surgeon to manipulate content interactively while their hands and eyes are busy with the operation procedure proper. And notice how you can, just turning your head, access freely data sets containing medical images from the patient that the surgeon is operating, while keeping more ergonomic positions, and that improves the procedure. So moving on, I think, how am I doing with respect to time?
Sir, you might wind up in another 5 minutes.
Oh, I thought that I'd been going on for 20 minutes. Maybe I'm wrong. Okay.
Yeah, actually around 40 minutes is over. It started around 3 o'clock. So maybe another 5 or 10 minutes, sir, it may take. We are actually enjoying our session, so you may take another 10 minutes also.
Thank you. Okay, so let me gloss over rehabilitation and maybe skip some of the work that we've done in terms of using augmented reality to improve rehabilitation movements. The idea is to help the physicians
after injury or surgery. This is often performed in co-located sessions with a physiotherapist who will diagnose and prescribe exercises to restore strength and range of movement. During these sessions, the physiotherapist provides immediate feedback and correction to ensure the patient is performing the exercises correctly. But when the patient is at home and must perform their exercises away from the physiotherapist, they do so without corrective guidance and are at greater risk of re-injury or slower recovery. To explore this problem, we developed Physio at Home, a Vicon-based prototype to explore the use of visual guidance and feedback techniques.
So here you see a form of augmented reality in which the patients see themselves in a mirror.
Called the Wedge, and multiple camera views from
And,
the front and top to show detailed depth information.
This is an idea
Speed or range of movement of an
on
exercise by using an arc to convey the body plane the limb is moving on, and an arrow to show the direction it is moving in.
So the idea is that you can use augmented reality to provide guidance even without the presence of the physiotherapists.
We also make use of the top-down camera view of the wedge to show the extent of movement and how far the patient is deviating from the exercise's plane of movement. We ran a study using 4 shoulder exercises from physiotherapy to evaluate the effectiveness of our wedge and multiple views. We compared how accurately participants could follow these exercises when using a single frontal view with either our wedge or video playback, and when using multiple views with wedge or video. Overall, we found that participants could follow exercises the closest when using our wedge with multiple views, and we identified several characteristics required for accurate movement guidance and challenges for exercise guidance systems.
Okay, moving on, we did try the idea of projected augmented reality, and I'm going to move on quickly to this idea of providing movement guidance. So the whole process is doing a recording by the physiotherapist that provides movement guidance to the person, having cameras to watch how they perform the movements, and then they give online feedback. And here you see another interesting work that we published a couple of years ago too on how using a projector augmented reality. So you have a projector on the ceiling that provides feedback during the execution of a movement as prescribed by the physician. Since I'm a little bit short of time, I won't give you details about how we provide 3D feedback and the position of the elbow, the arm, and the forearm in real time, but you can get an idea from the visualizations and then from the perspective of the movement and how you can provide feedback about how well the movement was really done. And this is an example with a better performed movement or some errors that are done. And you can see different visualizations that we can use to help people. Okay, well, there was a big error there, and we provide image, and then the final example is how you can execute the movement almost perfectly, and how you can get post-movement feedback on its performance. And green circle means that you are doing well. And so this is the basic idea. So you got 100% there. And the last example that I would like to show for the person who asks whether you can use augmented reality in using mobile computing contexts. Here's an example using smartphones and mobile augmented reality. The idea is to help people using crutches, using a worn projector and camera, not cameras, but just a cell phone, to input the condition of the patient and to guide them in using crutches. And this was developed by a woman that had no previous computer science or coding experience, but she had experience using crutches and using, with the help of physical therapists, she developed a mobile application that allows people to answer questionnaires, having a body-worn projector around the waists, and then walk with projected visual cues. You see the projector here. Here is the projector worn around the waists, and here is the image that it projects on the floor. And this is an example. So people answer a questionnaire on problems that they have, whether say that the problem is the right or the left foot, what kind of what's their height, and what is the foot that they cannot exercise the weight, connect the projector, and then this is what they see as visual cues. And you get indication of which foot should be set forward. And this is indication of the instructions that they get projected in front of them. People actually like this. They said it was effective in terms of learning, and this was a master's thesis project. So I hope that this answers effectively the question about using mobile augmented reality effectively. So are we there yet? No, there are many challenges. What are the challenges that you have to use virtual and augmented reality in medical applications? Well, for one, we are in a situation similar to many years ago where we have non-standard equipment. Each different set of oculars or head-mounted displays comes with a different user interface, and it's difficult to adjust the equipment. In terms of user interfaces, I can say that virtual and augmented reality are at the same stage that the automobile was 150 years ago, where people were still experimenting with handbrakes, where you would turn the wheel left so that the wheels would turn right and vice versa. And that can induce disorientation, fatigue, and sometimes nausea in the patients. But I believe we have a bright future ahead with a combination of Internet of Things, perception-based techniques, improving in ergo and hygiene, and addressing multi-format images and multimode user interfaces, and perfecting gestural languages. So this was part of a work called IT-MEDEX that I presented to you, interactive tablets for collaborative scenarios related to 3D medical images. You can scan this image, and in case you're thinking, we have many people that develop many of the works that I described here, and this is some of the members on our team. And I'm open to questions right now.
Okay, thank you very much, sir, for your wonderful presentation on the use of virtual and augmented reality in medical diagnosis, rehabilitation, surgery, and so many applications you have shown us. So, sir, you have already answered some questions. I'll still ask once more to the forum that if there are any other questions, you can please write in the chat box or even unmute yourself and put up your question. So I can't find anything more in the chat box. The questions earlier were already answered.
Well, if nobody questions, there are no forthcoming questions, feel free to email me at this address, jorgej@acm.org. And there's a bunch of bibliography out there that you can consult on these topics. So if anyone wants to know more.
Okay, so thank you, sir. I don't find any more questions, only acknowledgements that it was a wonderful session, excellent session. Some chat box, I can see only some acknowledgements. So perhaps then we can end this session. And before just ending, I would again request Professor Dibakar to present your screen so that we can facilitate Professor George with the virtual memento.
Sir, can you please stop sharing so I can share? This is Sarah is sharing. Okay.
Yeah.
Now it is visible?
Not yet.
Not yet.
Yeah, now
Yes.
it's
Yeah, now visible.
yeah. So, Professor George, so this is for you in this pandemic situation. We have this virtual memento for you. And anyway, it was a very wonderful session, very informative session. We all enjoyed. We can see from all the acknowledgements in the chat box. So thank you once more for this nice session and for taking time for us to be in this conference. Thank you.
Thank you.
So over to you, Tina ma'am, now.
Yeah. Am I audible?
Yes, ma'am.
Yeah. Thank you, Professor Ghosh, for chairing this session. We are extremely fortunate to have such speakers among us who are stalwart in their own field, contributing to scientific revolution across the globe. I'm quite sure that the young minds present in this conference can extract the maximum out of the entire series of lectures covering broader scope. Hence, the conference name Spectrum is truly justified and it actually does justice in its naming convention. Thank you all for joining us. This marks the end of Technical Sessions 3 of Invited Talk Series.
So, Professor Tina, are we starting the valedictory here itself, or we join?
No, we will be doing the valedictory here itself.
Yes.
Professor Rai Chaudhary and Basu, can we start with the valedictory right now?
Yes, yes, ma'am.
Yes, we can. Okay.
Okay.
Welcome back to the valedictory session of 3rd International Student Conference on Current Advancement in Science and Technology, Spectrum 2020, organized by Department of Basic Science and Humanities, Institute of Engineering and Management, Kolkata, India. Spectrum has now been coined as the flagship event, which is indeed a proud moment for all the members. Going deeper into its terminology, we find a close resemblance and relevance with the electromagnetic spectrum, where violet end represents science and the red region predicts technology, and all the other colors of the visible region represents different segments of science and technology that it covers. This conference has gained visibility since its inception, and every year it changes its color with new and innovative inclusions in its formulation. This year it has grown by leaps and bounds by virtue of the quality of its lectures, the wide range it has traversed, starting from the innovation ecosystem to overcome farmers' challenge to virtual and augmented reality in healthcare. The conference went a long way to motivate young minds and provided them a global platform for all the communities it catered. Not to forget that the contributed oral session were also witnessed a series of innovative ideas and presented over a wide range of topics. As far as the journey is concerned, it is about 3 hardworking individuals at 3 different geographical locations, working under the able supervision of Professor Arun Kumar Bor, Professor Prabir Kumar Das, and Professor Koel Ganguly. Of course, there have been many more to contribute to the overall experience in bits and pieces to lay its foundation. Not a single day all the conveners met physically to chalk out the entire plan of execution. Entire planning was done, undone, and redone over the virtual platform with 2 small students team. One is that of a web developer and the other is the publicity team. Every one of us had our own expertise to get that particular job done with the utmost precision and accuracy. Types of our jobs were generally non-overlapping in nature, but actual validation was confirmed after concatenating every bits and pieces. Our sincere gratitude to Professor Dr. Arun Kumar Bor, Conference Chair, Spectrum 2020, for his valuable suggestions in framing up this conference since its inception. He has been a true torchbearer and spearheaded this conference from the forefront. On behalf of the organizing committee, we thank our President, Sir, Director, Sir, Principal, Sir, all Deans and HOD of IMEM Group and the entire department to stand as pillars beside us to witness this day bigger and brighter from a distant dream. May I request Professor Dibakar Roy Choudhury, Convener 2020, to show us a short video about the journey of Spectrum 2020.
Okay, I am just requesting Biprojit Dasgupta, our student coordinator. He will share the video. Biprojit, please share the video.
Yes, sir. Am I audible? I will start sharing the screen once.
Yeah,
Yes,
you
yes,
are audible.
Yes.
Yes, sir. I am starting. So is my screen visible?
Yes.
Yes. Thank you, Brojit Pal, EC second year, for making this awesome video.
Heartfelt thanks to the students sparing their valuable time and putting in their best with the unparalleled guidance of Professor Dibakar Roy Choudhury and Arnab Basu. May I now request Professor Dr. Koel Ganguly, Chief Coordinator, Spectrum 2020, to summarize the whole event.
Okay. Thank you, Professor Tina Dey. Am I audible?
Yeah, you're perfectly audible.
Okay. Thank you, Professor Tina Dey, for giving me this opportunity. So good afternoon, everyone. It's time to summarize the 3rd International Students Conference on Current Advancements in Science and Technology, Spectrum 2020. Now, being one of the initiators of this very idea of Students Conference, so right from its beginning when it started in the year 2014, so I would like to state briefly the history of this conference before I summarize this year's conference. So in the year 2014, our director, sir, Professor Dr. Satyajit Chakraborty, he gave us the idea of organizing a students' paper presentation competition among the students of IEM. So that time, myself, Professor Shamapika Dasbishaj and Professor Paramita Mukherjee, under the able guidance of Professor Arun Kumar Bor, now Dean Engineering IEM, we started this paper presentation competition. And it was on a much smaller scale where only the students of IEM participated. Then in the year 2016, we took it to a little bigger dimension where we had students from all around the colleges of West Bengal, reputed colleges of West Bengal, participating in this event. And in 2016, we coined the term Spectrum for the first time. Then in the year 2018, from the year 2018 onward, we started with the International Students Conference. We took it to the global platform and we gave it the name International Students Conference. And we had Spectrum 2018. And since then, Spectrum has grown much bigger and broader every year, and we are involving more and more global participants and speakers. So in this year, Spectrum 2020 has a galaxy of speakers enriching us with their research ideas. So we had Professor Wim van Haverbeek from Surrey Business School as a keynote speaker. He talked about digital technologies and innovation ecosystem. We had the opportunity to hear to Professor Valentina Balas from University of Arad, Romania, speaking about fuzzy logic. Day one ended with a brilliant lecture by Professor Thomas Webster on application of technology to combat the COVID-19 pandemic. On day two, we had an exposure to the spinner innovation model by Professor Ronnie Figueredo of University Europea, followed by an informative session on carbon nanotubes by Professor Albert Nasibulin of Institute of Science and Technology, Russia. Today, just before this valedictory session, we were privileged to enrich ourselves with lectures by two eminent speakers, Professor Vivek Polshetivar from TIFR and Professor Joaquim George from University of Lisbon, Portugal. Now, apart from lectures by scientists all around the globe, Spectrum 2020 has provided platform for the undergraduate, postgraduate, and PhD students to showcase their innovative ideas. The essence of this conference is that it covers the research fields from almost every domain. So brilliant presentations were given by participants in the contributor sessions in the field of physics, mathematics, computer science, environmental science, biological science, nanotechnology, electronics, and whatnot. So from the behalf of this organizing committee, we are really thankful to our speakers for spending their valuable time with us and enriching us with their research ideas. And of course, the participants from all over India and all around the globe, they were brilliant in their presentations. So I'm sure in all these 3 days, we were enlightened by the research currently going on throughout the world. So before I end this the summary that I am doing, I would like to express my gratitude to our director, sir, because it's his motivation, our inspiration that motivates us to make this conference go bigger and broader every year. And of course, Professor Dr. Arun Kumar Bor, the pioneer of this conference, and he has been guiding us since the year 2014. Like, we cannot imagine Spectrum without you, Arun sir. And of course, our head Department of Basic Science and Humanities, Professor Prabir Kumar Das, he is always there for any and every kind of help you ask from him regarding Spectrum. And of course, he's with us for every conference that goes on in our department. And kudos to the 3 pillars of this conference, Professor Arnob Basu, Professor Tina Dey, and Professor Dibakar Roy Chaudhary, because it was a challenge this year to make this conference successful in the online mode without meeting physically and arranging everything in the online mode. It was a real challenge. So with this, I would like to end, and I wish that next year Spectrum will be even better and even wider and broader. Thank you. Thank you, Professor Tina.
Thank you, ma'am, for your presence and your valuable contributions to this entire journey. Next, I would request Professor Dibakar Roy Chaudhary, convener Spectrum 2020, to announce the award winners of Spectrum 2020. Over to you, Dibakar sir.
Thank you, Tina madam. So before going to announce the name of the session winners, I would like to say that all the participants have given their best and they present very well. But according to the rule of any competition, we cannot declare all winners. So here I am going to announce the name of the winner of each session respectively. So at first, the first session, that was the theme of the session was nanotechnology and environment science. The winner is Sachin Kadian and Gaurav Moinak from IIT Roorkee. The title of the paper was Effect of Heteroatom Doping on Fluorescence Quantum Yield of Graphene Quantum Dots for Optical Sensing Probe. So a big round of applause for Mr. Sachin.
Yes, please, please make your video on.
Yes.
And it will be a virtual appreciation to understand that.
Thank you, ma'am. Thank you, sir.
Okay. Okay, I'm just now moving forward to the next session. That was the theme of the session was mathematics and electronics. The session winners are from IIM Kolkata, Tanishta Pal, Farhan Khan, and Raunik Rai. The title of the paper was Development of a Universal Running Time Predictor Using Multivariate Regression. A big round of applause for Farhan, Tanishta, and Raunik. So please, can you open your front camera, please? Farhan, Tanishta, and Raunik.
Yes. Please make your video on. This is such a delightful moment for all of us here.
If you are there, Farhan, Tanishta, or Raunik. Okay, I think they are not here.
They are not here.
So I'm just going to the next session. That theme of the session was Computer 1. The winners are also from IIM Kolkata. The winners are Ujan Chaudhuri, Hindal Sen, Shomoditya Sinha, and Devdeep Dasgupta. The title of the title was Can Artificial Intelligence Beat Video Games and Analysis? So a big round of applause for them also. So can you open Ujan here, Hindal and Devdeep, your front camera?
Yes. You can open that.
Sir, I'm the only one available here. My rest of the teammates are not in the session actually.
Okay, congratulations, Devdeep.
Thank you so much, everyone, sir. Especially to the judges. Thank you so much.
Okay. Now the next session was biological science and social science. So winner of the sessions also from IIM Kolkata, Shamoita Kali, Mehuli Chakraborty and Saushrabdi Dash. The title of the paper was Digitalization in the Wake of COVID-19 and Analysis. So I just request to Shamoita, Mehuli and Saushrabdi, just open your video camera and just say something.
Are the students present here?
Shamoita, Mehuli and Saushrabdi, you are present here. If you can don't open your camera, then you can just say something also.
No, I don't think they are there.
Okay. So let's just go into the next session. That the theme of the session was physics. The winners are from University of Hyderabad, Devika Devnath, M. Jahid Malik, and Ashok Chatterjee. The title of the paper was Metallicity at the Crossover Region of the SDW and CDW in One-Dimensional Holstein-Hubbard Model with Gaussian phonon anharmonicity. So I just like to say, Devika madam, if you can open your front camera or say something. Devika Devnath, Ms. Devika Devnath.
Are the presenters present here? Please unmute yourself. Please unmute yourself. Devika, can you hear me? Yeah. Now say a few words.
Thank you so much for the award, and thank you also for organizing this beautiful conference in such scenario of pandemic. Thank you.
The last session, that the theme of the session was Computer 2. The winners are from CSIR National Physics Laboratory, New Delhi, and Academic of Science and Innovative Research, Ghaziabad. So the winners are Pradeep Kumar Kashyap and Bipin Kumar Gupta. The title of the paper was Study on Graphene Ground at Low Pressure by Chemical Vapor Deposition for Device Fabrication for Quantum Hall Resistance Application. So please, if you can open your video camera and say something. Mr. Pradeep Kumar Kashyap and Bipin Kumar Gupta. Yes.
Mr. Pradeep, please unmute yourself. We are not able to hear you properly.
And if possible, open your video also.
Yeah.
Hello?
Yes.
I would like to say that thanks to all the judges for this award, and I'm very thankful for that, and that is the great opportunity for me to be here among all of you. Thank you very much.
Okay, thank you. Now I'm just going to the most important part of the conference, that is overall winner of the all the sessions. That is the theme of the session. We actually get the winner from the theme of the session, that is physics. So the winner is from University of Hyderabad, Devika Devnath, M. Jahid Malik, and Ashok Chatterjee. So I just once again want to say Devika ma'am, yes, if you share something about this.
Yes, if you can unmute yourself.
Yeah, I mean, what may I say? Like,
you're running out of words.
Yeah, no, actually, I haven't understood. Like, this is the felicitation, like, or what? I didn't get it.
It was the best paper from your session of physics and the overall as well.
Oh,
coming from
okay.
all the sessions together.
Oh, thank you so much. That's a big thing. Thank you very much. Actually, I was typing, so I just missed your words. to hear. So thank you so much.
Okay. So one information I have to share, that is we will mail the e-certificates between 2 to 3 days. So, and we will also provide the winner's trophy after this pandemic situation is over, and that will be informed via mail.
Okay, thank you very much.
Okay, now I'm just going to announce the name of our dedicated volunteer team. Without their continuous effort and support, this conference would not be so much successful. So we are very much thankful to them. So at first, I'm just calling their name, and I'm requesting everyone to just, if it is possible, can open their front camera and say hi. So first one, Ognibo Chatterjee, EC third year. He is our web developer and event organizer head. Ognibo is there?
Ognibo.
Okay. Next, Biprojit Dasgupta, our EC's third year, technical team head. Next, Anish Pine. Thank you, Biprojit.
Thank you to the teachers for giving me the opportunity to work for the conference, and congratulations to all the winners.
Thank you, Biprojit.
Thank you.
Next, Anish Pine, our EEE third year, our publicity team head. Anish is there? Okay. Now I'm just moving forward. Brojit Pal from EC second year. He is our graphic designer, and he made this awesome video. So I would like to request Brojit to open. Yes, Brojit.
Thank you, sir. It was really a pleasure working for Spectrum 2020.
Okay.
And
Next.
more we will work together in the upcoming conferences.
Yes, sure, ma'am.
Next, Devashish Shaha, second year. He is our YouTube live streaming handler. So I just request to Devashish, can you just open your front camera?
Yes, thank you, sir, for giving me the chance, and thank you for giving me the chance for handling of the YouTube live streaming, and I will do it in the forward conference.
Okay, thank you, Devashish. Next, Shalini Bhattacharya, ECE second year. He is one of the event organizer, also the member of the publicity team. So Shalini, can you? Shalini is there?
Sir, can you see?
Yes.
Yes, thank you, sir. Thank you so much for this opportunity, and looking forward to work in more conferences for the college. Thank you so much.
Next, Pritha Ghosh. She is our online attendance tracker, also the member of the publicity team. So Pritha, are you there? Pritha Ghosh. Okay. Yes, Pritha is writing. Yes, sir, I am here. Can you say something? If you can open your camera, you can also say something also. Okay. Her mic is not working. Next, Shayantan Dasgupta. He is also our online attendance tracker and also the member of publicity team. He is not present now. Actually, now.
Sir, I am here, sir.
Oh, Shayantan is there. Okay, Shayantan, please say something.
Sir. Hello, sir. Thank you for giving me the opportunity to work, and looking forward to work in many more conferences. Thank you, all the teachers.
Okay.
Thank you, Shayantan.
Next, Venisha Odhikari, second year. He is also the part of our publicity, also the reporter of our contributed session. Venisha is there. Venisha is there. Okay, I think Venisha is not there. So I'm just going to the next one. Shashwata Shah, third year. She also the event organizer and so also the member of our publicity team. I think Shashwata is not there, so I just moving forward. Shubhrajyoti Majri, mechanical department, second year. He is also the member of our publicity team. Yes, Shubhrajyoti. say something?
Thank you, sir, for giving me this opportunity, and congratulations to everyone who won the trophy and for paper presenting. And thank you.
Okay.
Next year, you also need to acclaim one.
Okay, ma'am.
Next, Shayuni De, EE second year. He is one of the event organizers, also the member of the publicity team. So Shayuni, are you there? Shayuni De. Okay. Shayuni, I think, is not present, or his or her mic is not working. So next, Rohini Dasgupta. He is one of the member of our publicity team. So I just I request Rohini to open your camera and say something.
Thank you so much, sir. It was really a great experience to work for Spectrum. So thank you for the opportunity and congratulations to all the winners.
Okay. Thank you, Rohini. Now just over to Tina Madam.
Thank you, Professor Roy Choudhury. Both the other conveners of Spectrum 2020, Professor Arnab Basu and Professor Dibakar Roy Choudhury, both are true performers, and it was a pleasure working with them. Now I would request Professor Kamakha Prasad Ghatak, Senior Professor and Research Director of IMEM Group, to give the vote of thanks and officially announce the end of this event. Date of the next year Spectrum could not be announced now due to a lot of intervening factors. Stay tuned, stay safe. See you all in the next version of Spectrum in 2021. Till then, this is Dr. Tina De signing off. Over to you, sir.
Tina, can you hear me?
Yes, sir, of course. You're visible as well as audible.
I am extremely grateful to the beloved organizer to choose me at this age for this beautiful valedictory speaker. Actually, with respect to vote of thanks, I must say that our director, sir, our president, sir, Vishwajoy Chatterjee, vice chancellor, sir, also, together with Green Research Associate, helped me a lot, and actually they are my inventors. Professor, vote of thanks should go to Professor Arun Kumar Vaid, who is the instrumental and key person behind all Spectrum since the inception of this very beautiful topic in 1914, when Professor Koel Ganguly summed up everything in a very nice way, together with Professor Arun Vaid, started from the inception. The baby is now reached the youth with the hands of very beautiful physics teachers, all the beautiful students, and obviously all the other persons who are going to do it. We are extremely grateful to all the organizers. We are grateful to Professor Wim van Haverbeek for his beautiful talk on digital technologies, new business model, innovation ecosystems, and systems goes on. Vote of thanks must be goes to Professor Valentina Emilia Bias, the last, because he gave a beautiful lecture. She gave a wonderful lecture. I have heard it totally. Advanced soft computing method, design, and applications. Thanks goes to Professor T.J. Webster, who is Professor of Chemical Engineering of Boston, for his wonderful talk, Green Nanomedicine, Implantable Sensors, and Nanotechnology even in fight off instead of COVID-19. Professor Ronald Figueroa for his wonderful talk, Spinner's Innovation Model, and Professor Albert Nasibulin for his carbon nanotube from synthesis and applications from Russia. For Russia, I have a peculiar idea. When you got to at 19, I got in touch with the famous Landau Lipschitz 12-volume series, and therefore Russia is always a beautiful thing for me. Although I go there, went there for many times. Then Professor Paul Settiwer, who is a TIFR professor, who again talked on nanotechnology to combat clinical changes. The system goes on, and we are also very grateful to Professor J. George, wonderfully gave all lectures. I sometimes think, though he is a professor of the Department of Computer Graphics and Multimedia, School of Engineering, University of Lisbon and Portugal, with a beautiful talk, approaches and challenges to viral and augmented reality in the healthcare. I think at the same time, he's a good computer scientist, wonderful teacher, and a wonderful doctor, the way he's doing so. Many things in a single body, 3 in 1. All of us have heard the name of Professor H.J. Dyson, the famous trio, who said that quantum electrodynamics by Professor Feynman, unforgettable Feynman, together with Schrödinger and Tomonaga are basically same. Though they are using different method, results are same. That person, wonderful professor, 67 years full professor of the Institute of Advanced Studies, Princeton, unbelievable, who wrote a book, wonderful book, all of you know. Name of the book is Infinity in All Direction. By hearing this with our wonderful students and unparalleled speakers, infinity in all directions, the system goes on, infinity in 360-degree directions. With the beautiful lecturers, wonderful speakers, with our very beautiful students, because I believe we are the teachers by the students, for the students, of the students. We exist since they exist. The reverse of the theorem is not true. I have very, very high hope with the wonderful lecturers and wonderful speakers. Our students can go to horizon. Who knows that in one day, our dear students and wonderful teachers will not obey, will not go to Dirac medal or Fields medal. Maybe the future Ramanism is in front of us, a future Landau, a future Dirac. Who knows the thing? Now, when I came to age, I see all science, engineering have a synthesis. They are not different. Nature is totally integral. Nature does not know science, engineering, arts, commerce, anything. He only understands that he has a problem and he has to solve it. Nature has got only 2 formulas. My dear friends, you will not believe. If there are 2 quantities A and B, either A is equal to B or A is not equal to B. Believe me, all your science, engineering falls on this. Your Schrödinger is nothing but some Schrödinger operator into psi equal to 0, put this equal to A and put B equal to 0. You go on Dirac, same thing, Dirac operator into psi, put B equal to 0. Put A equal to V, V equal to Ri, it is V equal to Ri, it is your famous Ohm's law. Anything you see, anything you do, anything you purchase, and nothing but of 2 qualities. Nature has got only 2 equations. One is either A equal to B or A is not equal to B. Where you go to the famous inequality, mainly done by our Ramanujan, that inequality genius of the world. The system goes on and on. Again, last time what I feel, my dear students, object being same, observer being different, interpretation being changed. You may say, how come? What you are telling, Professor? An electron is an electron. Before your de Broglie, it was particle. Some says it is wave. De Broglie's equation, lambda equal to h by p, says it is the GANs of Shivaji, that Ardhanarishwar Murti of Shivaji. Then system goes on. Pauli says, for Spain, add it externally. Dirac says, no. Spain is the consequence of my equation known as Dirac equation. Putin says, who is the world famous string theorist, all of them are wrong. Spin is the attribute of space. Everything comes out. If you solve Schrödinger equation in 5 dimensions, spin will automatically come. And it is the function of space only in its wonderful hyperspace theory. Thus, there is no final. Just searching, searching, and searching. Who knows what is the end? This system goes on and on. I have high hope that all of our students will do marvelous, because the baton is for them. We are old, we are putting every logic of creativity. Please remember Einstein, creativity first, creativity midnight, creativity last. Each and everyone is great. Of this conference, not only here, but all the students, all the speakers, specifically our management directors, all of them whose name I have told. only one life equation: mission equal to vision equal to passion equal to creativity. Mission equal to vision equal to passion equal to creation. Only one life equation. At the age of 67, I am now discovering. Nothing more, nothing less. Therefore, nothing is end. End is where we start from. We cannot say our spectrum is end. Spectrum, end is where we start from. From that very moment, we are thinking for the next spectrum. All great people will come. All great things will be done. All will be very much wonderful. There is no end of creativity, no end of any job. Only goes on and on until death is the end. That's all. I believe it's a wonderful success. With this, I stop at that point. Thank you, Professor Tina, for inviting me. And thank you, all the organizers in all ways. Many thanks.
Thank you, sir. Thank you, sir, for your inspirational words. Now we officially announce the end of Spectrum 2020. Thank you all. See you back in the next session.
Yes, thank you. Thank you. Thank you, Professor Tina. So,
Thank you. Great.
So we'll be ending Spectrum this year. Hope to have a bigger Spectrum next year.
Yes, in 2021,
Even bigger.
and that will be in the offline platform.
Yes.
Obviously,
Hopefully
Great,
we have
great.
it in the offline platform. Okay, and
Sure.
thanks to also the chairs of the different contributor sessions. So thanks to them also, right, Professor Tina? Thanks to them. Thanks to the audience. Simply audience also were there. The teachers of the Basic Science and Humanities Department. Just being the audience is also a great job. So thanks to them.
And just as we cannot think that on a Sunday afternoon, we are
Yes,
finding an
Sunday
attendance which is
afternoon,
almost touching
and so many
80.
teachers present.
It's a real great achievement because on a Sunday
Yes.
afternoon, when IPL is there, we are finding an attendance that is almost touching 80. That is also
Yes.
great. So it's a success from the entire team. And thanks to all for joining us. Hope to see you all again in Spectrum 2021. It will be announced shortly. Thank you all.
Thank you. Thank
you.
Thank you.
Thank you.
So we are leaving.
Yeah, we are leaving.
Can you please open your video camera so I can take a screenshot of this? All the organizer, all those who are present actually.
Yeah, you can take because I'm having a lot of technical glitches at my end. That is why I cannot put my video on for a longer point of time.
Okay,
And,
okay, no problem.
Just you take the photo because I am working with my data. My Wi-Fi is not working.
Okay. Wait, accept. Okay, just taking the screen. Okay, thank you.
Thank you all. See you all in the next year.
Thank you.
And that too will be hopefully in the offline platform with Spectrum much more bigger and with more colors. Thank you.
Thank you and goodbye.
Goodbye.